All right, so for this one, if you can remember, I said that we can set the 0 point for voltage to anywhere we want. And so we typically want to set it where it's easiest. And here, for point charges, when we're doing like the voltage created between these point charges, the easiest thing to do is set 0 at infinity and then start bringing in the charges one at a time. So if we start with all these charges all spread out way from infinity from each other, and we bring the first charge in, which I'll call negative Q there. So I'm bringing this one in first, okay? It's gonna take me absolutely no work to bring it in because there's no other charges near there. And so there's nothing to prevent me from moving it right to that spot. It's super easy. There's no resistance, no whatsoever. And so I don't have to do work against any other field from any other charges. So I'm done. Now, if you look at 2, I want to go ahead and bring in the second charge, which I believe I did this charge. Which charge did I do next? Well, I messed myself up here. I labeled them. So that's 3Q. So that's this one up here. I labeled it charge 2, but then also called it charge 3 because it was the 3Q one. So my red numbers are the order in which I brought them in. The numbering down here corresponds to their charge. So this is the voltage between charges 1 and the 1Q charge and the 3Q charge. So anyway, so I'm going to bring this one in next. Voltage is the work over the charge. So to bring that charge into that spot, I have to do work against the field that's created by charge 1. So this charge right here is creating an electric field over here pointed in this direction. And that's what I'm doing work against there. That's what I'm doing for. So I have to bring it in on that field. Now, that field is actually pointed in that direction. That's the force, because that's a positive charge and that's a negative charge. And so what's going to happen is it's actually going to want to go to that location pretty much on its own. So when I calculate this, I end up with doing some negative work there, okay? Or some positive work because it just did what it did. So I did voltage is work over that. So I just did, excuse me, that tells me work is the charge we're moving in times the voltage created by the first charge we put there. So it's the voltage from charge 1 at the 3Q charge. Then I just go ahead and I multiply that through. I've got negative 3Q, negative Q over square root of 2D, and then that ends up giving me this right here. So that's just the voltage created from this charge at this charge location and the work I have to do to bring it to that location. Next, I have to bring in this third charge. But now to bring in this third charge, I have to do work against both the first charge I put there and the second charge I put there. So when I bring that third charge in, I have to do work against between like these two, the 2Q charge and the 1Q charge. And I also have to do work against the 3Q and 2Q. And so that's what I did here. So I did it the same as I did before, just with the different ones there. And so when I calculate that one, I get these two answers. I get this here and this here. And so now I have these 3 amounts of work that I had to do to bring those charges in. And so the work against field. So then all I have to do then to figure out the total work is to add them all up. And so that's what I do here in this step right here. I go through and add those 3 all up. And it gives me, get rid of those squares, it gives me this amount right here, which is negative 3 over square root of 2k, q squared over d plus k q squared over d. However, that's the work, and work and potential energy are negatives of each other. Work is negative change in potential energy. So I come down one more step where I simply take the negative of it, and that's my answer then right there. I took the negative of it, and that's my total amount of potential energy there. So does that make any sense whatsoever?
Yes. I don't know. Yeah, that makes sense. I don't know really what I was thinking when I first looked at this problem, but like that makes sense what you just said.
Yeah, no, that's okay. It's kind of interesting because classically speaking, you can do this problem to figure out how much energy it would take to create, or not how much energy, to figure out what the radius of an electron is. Because if you assume an electron is, if you assume an electron is 9, what is it? Oh my gosh, I forgot that. 9.1 times 10 to the negative, what is it? What? Oh my gosh, I've forgotten the charge of the elementary charge here.
So the negative 31st?
I thought it was to the negative 19th. Coulombs. It's
the charge.
1.8, is that it? Why have I forgotten this number? Where's the elementary charge? I've forgotten the elementary charge. Anyway, whatever it is, if you figured out how much, so we essentially can look and see, thanks to particle colliders, we can see how much energy it takes to make an electron. So if you take that amount of energy and you see how closely you can force together this amount of charge, it should predict for you the radius of an electron, right? We're bringing that charge in. If you say it's spherical, you're bringing in all that negative charge together into this little spherical electron, right? And therefore you can figure out what the radius of an electron is. And the problem is, this is one of the great failings of classical electrodynamics, is that it's wrong. We know that the actual, or at least we've been able to detect that the actual radius of an electron is much, much smaller than what you get by doing that problem. And so it's a big failing where it doesn't work in that situation, which was always weird to me because it works so perfectly in so many situations, and yet can fail in a situation like that. Then suddenly it seems like if it works so perfectly, it should just always work, but it doesn't. All right, any other ones you'd like me to go over?
I'm pretty sure there's one more, but I'm trying to find it. Because I have like notes in 2 different places, so I was trying to find where I wrote that. Quick question. Is example 20-4, that one is right before that one. Are those similar? Or is that?
The situation is similar, but it's not asking us to find how much potential energy is stored in the system. What we're doing here is we're putting, if I remember correctly, we have this charge here and this other charge over here, and then we're going to put the 3Q charge there and then let it be free, right? Especially a third charge is released from rest at that location. So that third charge we're putting there and we're just going to let it go. So the electric potential due to the first 2 charges at that point, that's just figure out each one individually. So I did the voltage due to the regular Q1 and the voltage due to the 2Q1. And then you just add them up, which is the nice thing about voltage is it's scalars. You don't have to add them like vectors and worry about the angle. You just add them up. And so that got me what the total potential is at that point. It then asks me to find the potential energy of the third charge, not of the whole system, just of that third charge, which ended up being, all we have to do is do V equals delta U over 3Q, right? Delta U over Q, so potential energy per charge. And so that means that the potential energy is just the voltage that we just calculated in part A times 3Q. And so that's what that got me there, the 9 over square root of 2 times K Q squared over D. And then I don't think I ever actually calculated that in the second one because I did them in a different order. And then you come down here for the last part, it says, what is the kinetic energy of the charge when it has moved infinitely far away? So we let it go. It's going to repel away from those other two because they're all positive, right? And so as it repels away, it's eventually just going to get further and further away. It's going to speed up and speed up and speed up, but its acceleration is going to decrease because as it gets further away, the force gets to be less. And so it'll eventually get so far away that it's not really speeding up anymore. So it kind of will asymptote to a velocity, and that velocity would give you this, essentially all the potential energy would be gone, which means all the potential energy would have just become this kinetic energy, right? That's the conservation of mechanical energy. So like mechanical energy initial equals mechanical energy final, which is kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. So at the very start, it starts from rest. So that's 0, but we do have potential energy initial. Once it's infinitely far away, it's so far away, there's no potential energy anymore. And so it just tells us that our initial potential energy equals our final kinetic energy. So I just rewrote it.
So the reason why B and C are the same answer is because of the conservation of energy?
Yes, and because it starts from rest.
Okay.
So if it didn't start from rest, then this wouldn't have been 0 and we would have had to done something. And if say we only let it get like 10 meters away and not infinitely far away, then we could have had a final potential energy too. But at infinitely far away, starting from rest makes that 0. That's 0 because of starting from rest. That's 0 because we get infinitely far away.
And then I don't know if you've done all the questions, but the copy that I have from the Google Drive, the last, was it 3 or 4? The last 3 questions aren't done. Is that like we haven't gotten to that yet in the lecture?
Did it not?
Or did you just not?
No, it should have backed up. I did them. There. The last 3, that's these 3 right here, right? I did those this morning.
Oh, I don't have that.
Well, there's one. Want to screenshot it? And then after we're done, I'll check and see why it isn't backed up. And you picked the chapter 20 examples _ complete?
Yes.
Huh.
Yeah, I'm like, I didn't download this. I'm looking at it like through like on Google Docs or Google Drive.
Huh. Why isn't that backing up? Not sure why. Let me try this. Copy of it, and then let's incomplete. Did I spell that right? Come on. The underscore? Nope. Where's the underscore? All right, let's see if that'll back up now. Maybe that one will then end up in there. But do you want to look at those last three?
Yeah. Oh,
Yep.
it backed up now. They're there now.
Good.
Can we look at example 20-7?
That one? All right. So a person's heart undergoes ventricular fibrillation, a rapid uncoordinated twitching of the heart muscles. It often takes a strong jolt of electrical energy to restore the heart's regular beating and save the person's life. The device that delivers this jolt of energy is known as a defibrillator, and it uses a capacitor to store the necessary energy. In a typical defibrillator, a 175 microfarad capacitor is charged until the potential difference between the plates is 2,240 volts. What is the magnitude of the charge on each plate of the fully charged capacitor? So for this one, capacitance equals charge per volt, okay? And so then I just solve that for the charge equals capacitance times voltage, and that's the capacitance times the voltage right there, and I get that number right there, and that's it. And right here I worked out the units. A farad times a volt. A farad is a coulomb per volt, so the volts cancel on the left with a coulomb. So 3.92 times 10 to the negative 1 coulombs, or 0.392 coulombs. Then for the next part, it says what, so this is the amount of charge stored on one plate. The total charge stored on the capacitor is 0 if you count both plates, because one of them is positive and one of them is negative. So one of them has this amount of positive charge, the other has that amount of negative charge. Then here, find the energy stored in the charged up defibrillator. And so potential energy of a capacitor is 1/2 the capacitance times the voltage squared. And so that's all I did. I did 1/2 times the capacitance times that voltage squared, and that gets that. If I wanted to go through, I could have solved the first thing up there for capacitance and made it charge per volt, right? I could have used this right here. You can say U equals, because you're kind of looking at that and saying, hey, the total amount of charge on there, you know, the total potential energy had nothing to do with the total amount of charge there. But if I replace capacitance with Q over V from right above times V squared, you end up with 1/2 QV. And if you do that, you will also get 439 joules as well. So you can use that charge that we just found in part A to say it, solve it, and you'll get the same answer.
And then, so what, with little q, is that representative of a point charge, whereas like big Q is like a total type charge?
Yes, typically, yes.
Okay.
Typically, little q
I
means
know,
point
like,
charge, and big Q is like some chunk of charge in some sort of distribution.
Okay. Okay. Because I was like reading in the book, and yeah, it just kind of, got a little confused between, like, I didn't know if like big Q and like little q were like interchangeably, or like how the variables work with that.
It doesn't. You probably pretty much in most of the situations could interchange them without changing your answer, of course, because they're just a symbol. But yeah, typically they are used in the way that you said. All right. Any other things you want me to go over?
I think that's it. I think Some of the like later examples will probably make more sense after lecture tomorrow.
Okay.
So yeah, I think I'm okay.
Okay.
I wouldn't say good, but I think I'm okay.
You're getting there. All right. I'm going to pause this then.
I'm getting.
All right. So the only single student that showed up finished with their question. So I'm just going to run back through these real quick here, give maybe a little breakdown of them. For this one, we had a uniform electric field by 2 parallel plates and a capacitor there with a 12-volt battery. If the plates are separated by 0.75 centimeters, what is the magnitude of the electric field between them? Voltage equals E times D. Electric field times D, really negative, but they asked for the, really it should be negative ED, but they asked for the magnitude of it right there. We should highlight that. They asked for the magnitude, and so I don't care about the positive and negative sign then. And so just did, ED, so the electric field magnitude is just V divided by D, so 12 volts divided by that's distance across there. That's how much the electric field you'd have there. And so that's where I got that 1600 volts per meter. It then asks for a charge of 6.24 microcoulombs moves from the positive plate to the negative plate. Find the change in the electric potential energy for this charge. So it moves from that positive plate to the negative plate. So potential energy, remember voltages are change in potential energy per charge. So potential energy equals voltage times charge, just doing the absolute value here. All right. And so that's going to be the 12 volts times the 6.24 volts. And I'm only worried about the absolute value here because I know that this is moving the way that it wants to go. Therefore, if it's moving the way it wants to go, it is a decrease in potential energy. And so I go ahead and just put the final answer down here with that negative in it. All right. On the next one, we had, we were supposing the particle described in the preceding problem has an initial speed of 5 meters per second at point A. What is its speed when it reaches point B? So this is a conservation of energy. We know that mechanical energy initial has to equal mechanical energy final. And so kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. So 1/2 mv squared equals QA. That's all at point A. And then that's the first point over where it starts. And then 1/2 mv at point B squared plus Q and the voltage at B. So I subtract that QV over to the other side, and I subtract this one over and I solve for VB. So I just do algebra, solve for VB, get it right there, and then plug in numbers. I didn't finish plugging the numbers in. You can type all this into a calculator and get the answer, but that should be the answer for you for how fast it's going when it reaches there. All right, and it asks for speed, which is what we're going to get when we're messing with kinetic energy anyway, because the velocity gets squared and we'd lose any knowledge of the direction. Here we have a charge in example 20-1 is released from rest at the positive plate and that it reaches the negative plate with a speed of 3.4 meters per second. It asks us then, what is the mass of this charge and its final kinetic energy? So the mass of it is simply, again, conservation of energy, of mechanical energy. This time we're starting, the initial kinetic energy is 0. So that's 0. And I again go and solve. This time I'm solving for the final kinetic energy, but instead of solving for velocity, I solve for the mass since I have the final velocity and everything like that. And so it's just a matter of doing some algebra to get to there. And then you get this answer as your final or as the particle's mass. Then to find its final kinetic energy, it's just a matter of plugging that into 1/2 mv squared. We know what the final velocity is. It was given to us 3.4 meters per second. And we just found what the mass was. So plug that in and that will get your answer. You can type that in and whatever you're going to get. You're going to get like maybe 6.5 times 10 to the -5 or something like that. as your answer. This one, a charge Q equals 4.11 times 10 to the negative 9th coulombs is placed at the origin, and a second charge equal to negative 2Q is placed on the x-axis at the location x between x equals 1 meter. Find the electric potential midway between the two charges. So that's right here in the middle at half a meter from both of them, okay? And so I just calculated the voltage due to the positive charge, which will be a positive right there. And then I calculated the voltage due to the negative charge, which will give me a negative there. And then I simply added them together. All right, now these are point charges. So we're essentially calculating the voltage as though we were calculating it from out at infinity, where 0 was infinity. That's what happens when we use this KQ over R equation, is we're setting infinity equal to 0 voltage. And then when you're really close to it, the voltage, you know, goes up or down depending upon whether or not it's a positive or negative charge. So since we have a positive charge, the electric field is pointed out away from it. That means as we move in closer to it, we have to increase voltage. For the negative charge, that would be a decrease in voltage. So we end up with a negative 73.9 volts there when we do when we add those two together, one positive, one negative. If you look at part B, it asks for the electric potential vanishes at some point between the charges. And so essentially we want to find the place between them where their electric potentials exactly cancel out. So I called that some spot X like this. I said it's going to be a distance R from the positive charge and a distance of 1 minus R from the negative charge, since the whole length is 1. Then I just went through and put those in right here with our point charge potentials, KQ over R and K times negative 2Q over 1 minus R, and they have to equal 0. So we need the value for R that will make that 0. And then it's just a matter of going through and doing some algebra to make them work. So one of these was negative. That means that, zoom in here a little bit, that means that KQ over R equals K2Q over 1 minus R. I can cancel out the K's, I can cancel out the Q's, and you end up with 1 over R equals 2 over 1 minus R. You know, you can cross multiply, go in, solve for R, and it's 1/3 of a meter. So it's 1/3 of a meter there. So it should have maybe been drawn over here. Absolutely, it should have been closer to the positive one, but I drew it over on the other side. So really that X is somewhere over here. Okay, but that's that answer. This one, I believe I just went over in with that student that showed up here. I went over that one too. This one, a parallel plate capacitor is constructed with plates. It gives you the area of the plates. It tells you their separation. It says find the magnitude of the charge on each plate of the capacitor when the potential difference between the plates is 20.1 volts. So the capacitance of a parallel plate capacitor is epsilon naught times A over the separation, over D, the separation between the plates. That's your total capacitance there. But that capacitance also is defined as charge per volt. So that means we can say that epsilon naught times the area of the plates over their separation equals Q over V. And so if you go through, do some algebra, solve for Q right there, and then just start plugging in those numbers. Okay, so you plug in epsilon naught, plug in the area that was given, plug in the distance that was given, and plug in the voltage that was given, and you should get this result right there. That's the total charge on the plate there. And then it says, and it's a charge on each plate. One of them would be positive, one would be a negative version of that. And then here it says, what is the magnitude of the electric field between the plates? So electric field, remember voltage is E or negative ED. We only care about the magnitude here, so we can just say the magnitude of E equals just V over D. Don't worry about the negative or positive signs. And so that gives me the voltage is 20.1 volts. That's right there. And the separation D is, so that's how far it is between the plates, is that 5.5. Plug them in and you get your answer right there. All right, so this one says a parallel plate capacitor is constructed with plates, same area as the last one, same separation as the last one too, I believe. The space this time between the plates is filled with a dielectric. This is something that essentially magnifies our electric field and therefore increases the capacitance. When the capacitor is connected to a 12-volt battery, each of the plates has a charge of 3.62 times 10 to the negative 8 coulombs. What is the dielectric constant? So that's that property of the material. It's like electrical properties, how basically how well the electric field can kind of like flow through it. And so we take care of this by adding this extra kappa term right there for the dielectric constant. And we end up, that's just going to make it bigger. Of course, for a vacuum, that K would just be 1, and we wouldn't have to worry about it. But here, it's not 1, and so we do worry about it. Okay? Now, all we have to do is solve this for the dielectric constant right there. And again, it just equals Q over V, just like in the last one. So we simply solve it for K and plug in all the numbers they gave us. Well, we have epsilon, which we should know that one. The 8.85 times 10 to the negative 12. They told us the 12 volts. They told us the area of the plates. They told us the charge on the plates. They told us the separation of the plates. So it's just plugging in all the numbers that we were given or that are known, and you should get 6.7. Okay. Next one, this one I just talked about earlier in the video, so I won't go over that again. And then I think this is the last one here. It says the electric potential at point B in the parallel capacitor shown in the figure on that page 694, I drew it right up here, is less than the electric potential at point 4.5, at point A by 4.5 volts. So that means we'd have a drop going from A to B. So A is higher than B, which makes sense because in the picture, A is closer to the positive charge, right? This is the positive side up here of the parallel plates, and this is the negative side over here. Since the electric field goes out of a positive and into the negative, that means this one up here is positive and this down here is negative, okay? So, and then as we move along that electric field, we have to be decreasing our voltage. So that's a voltage drop from A to B of 4.5 volts. And the separation between points A and B is 0.12 centimeters. And the separation between the plates is 2.55 centimeters. So part A, the electric field within the capacitor. So find that. Well, again, voltage equals E, negative E times D. In this case, I wrote delta S because that's what I labeled that distance between the points A and B as. That's delta S. And so if I know the voltage between those points and I know how far apart they are, I can solve for the magnitude of the electric field, which is E equals V over that delta S. So this is the 4.5 volts over the 0.12 times 10 to the negative 2 meters. And then that just gives you 37.5 times 10 to the second volts per meter, or 3,750 volts per meter. Then for the last one, part B, it asks us to find the voltage difference between the plates. For that, we step back to V equals ED, the same equation, but in this case, I'm using D instead of delta S because I'm looking at the separation between the plates. I now know what the electric field is between the plates. I just found that in the previous question. And so then I used to figure out that electric field over this distance between the plates would create what kind of a voltage. So it's just the electric field I found in the previous part, which is the uniform electric field between the plates, times the separation between the plates, and we should have a 95.62 voltage drop between the plates. Okay, all right, I think that is it for this section. I know I went through those kind of fast, but it's a video, so pause it, rewind it, play it over and over again, listen to it, and if we have any other questions, then you'll have to ask me then the next time we meet. All right, that's it. Thanks a lot.